Okay, so back here on slide 34, now that we've got MM1 constructed, we're going to construct M1, which is a map from char to int, from the pairs contained within MM1. Now the map from char to int is still using char as the key, but this time multiple copies of the same key will not be allowed. And when we display the elements of M1, as we're doing here on slide 35, what we're going to see when we look at our first possible duplicate key, the L, notice that the first pair in which the key is an L, that is L3, is stored in M1, but then any subsequent pairs that have a key of L are rejected. Those are simply not stored into the map M1. So the pair L4 is rejected, the pair L1 is rejected. And so all we have in M1 is the first occurrence of the key L with its value 3. Likewise for O, we have the first occurrence of the key O with its value 5, and we see that in the output, but the second occurrence of O with value 9 is rejected. Alright, well, let me clean up my highlighting here on slide 34. So we have constructed M1 using the pairs taken from MM1, the multimap, from the beginning element up to but not including the end element of MM1. We now do the same thing to construct our unordered multimap from char to int using the values from MM1 begin up to but not including MM1.end. For the unordered multimap, the keys are in some seemingly random order, but duplicate keys are allowed. So on my system, when I run this, I happen to get key W value 8 as the first thing displayed. Then I get key O value 9 displayed, followed by key O value 5. Notice here that key O value 5 actually comes ahead of key O value 9 in the multimap MM1, but when we construct the unordered multimap UMM1 from MM1 and display the unordered multimap, the values come out in the reverse order for some reason. It's not predictable. You can't assume anything about the order in which these key value pairs are going to be displayed. Then finally, on slide 34, we have UM1, our unordered map that we're constructing from the multimap MM1. And this contains the same pairs as the multimap, except that duplicate keys are not allowed. So in this case, when the key value pair O5 gets put into UM1 as part of its initialization, the later pair, little o9, is rejected. Likewise, L3 is inserted into the unordered map UM1, but the later occurrences of L with their values, namely little l4 and later little l1, are rejected. Okay, so that's a quick look at the 4 map container types. We've now looked at all 12 of those container types back in our table. The sequences, vector, dec, list, and forward list. The associative or tree containers, set, multiset, map, and multimap. And the unordered or hash table containers. Unordered set, unordered multiset, unordered map, and unordered multimap. Alright, next on slide 37, we're going to take a look at another batch of operations that are common to most of these standard container classes, namely equality, relational, and assignment operations. All of the container types can be compared to containers of the same type for equality and for inequality. That is, you can compare a vector of int to another vector of int. You can compare a forward list of char to another forward list of char. You can compare an unordered map from string to double to another unordered map from string to double, etc. For many of the standard container types, you can also do relational or ordering comparisons. That is, less than, greater than, less than or equal, greater than or equal. You can do these for all of the sequence types and for all of the associative or tree-based types, but you cannot do this, as I guess ought to be obvious from their names, for any of the unordered types. So unordered set, unordered multiset, etc. are not able to do any of these ordering relational tests. Assignment is available as long as the object on the left of the assignment is of the same container and element type as the value on the right hand of the assignment. And you can also, in C++11, directly assign to a container from an initialization list contained within curly braces. It's also possible to swap the values of objects back and forth, either using a swap member function or using a top-level function named swap that takes two containers as arguments. Okay, so we're going to take a look at this now, starting with this code on slide 38. And on slide 39, we have the output produced by the code on slide 38. All right, there's nothing really tricky going on here on slide 38. v3 is a vector of char initialized with 6 chars, H-E-L-L-O and an exclamation mark. v4 is also a vector of char initialized with 5 char, capital H this time, followed by lowercase e-l-l-o. And v5 and v6 are empty vectors of char. Now, we can test whether v3 is less than or equal to v4, and when you compare vectors, comparison is done on an element-by-element basis. So the first thing that happens here is that the element little h in v3 is compared to the element capital H in v4, and it turns out in the ASCII character set, as you may have memorized by now, that all capital letters have lower values than all lowercase letters. So our test for less than or equal to fails immediately. Little h is greater than capital H, and so the output produced here is false. Then in the next statement, we are testing whether v3 is greater than v4, and indeed it is. Again, we only have to compare the first char of each of these vectors to discover that little h has a greater value than capital H. So what's displayed there is true. Here we're doing assignment so that v5 now contains a copy of v4, capital H, little e-l-l-o. Here we're doing assignment of an initialization list, which is a nice thing to be able to do. And next we're swapping the contents of v5 and v6. So v5 used to contain hello with a capital H. v6 used to contain lowercase bye, but now their contents are swapped so that when we display v5 in this red range for loop, the output that we get is by, whereas when we display v6 in this blue range for loop, we get hello with a capital H as our output. So a couple of quick examples of relational tests, assignment, and swap.